All right, my darlings. So let's do today a little bit of a review of lesson 8.01 before we move into radioactivity and half-life. The chemistry that you've studied so far has involved the reactions between elements and compounds, where one atom or group of atoms exchanges or shares valence electrons with another atom. In nuclear chemistry, however, you will study the composition and changes of the nucleus of an atom. So we're only talking protons and neutrons, not electrons. Nuclear chemistry began in the late 19th century and early 20th century as scientists discovered radioactivity and the subatomic particles that make up the nucleus. These scientists include Ernest Rutherford, Henri Becquerel, Pierre and Marie Curie, and James Chadwick. In studying radioactive atoms, they found that the nucleus itself could undergo changes. Nuclear reactions actually change the composition of an atom's nucleus, and if you change the composition of the nucleus, you are likely to change the element itself, right? Because the element's identity depends on the number of protons, so if you change the number of protons in the nucleus, it's not the same element anymore. So the nucleus is held together by three things: neutrons, which stabilize the nucleus, something called the strong nuclear force, which acts over short distances like neutron to neutron and neutron to proton interactions. And then number three, the residual strong force, which is the strong nuclear force between adjacent protons. So in a nutshell here, I know it doesn't look like a nutshell, but it's a nutshell, and you might want to pause the recording here and write this down word for word. But in a nutshell, the presence of neutrons adds a net attractive force to the inside of a nucleus. This force is called the nuclear force or strong nuclear force. The neutrons act like the glue that holds the nucleus together. If the nucleus does not have the right ratio of neutrons to protons, the nucleus is unstable and will then go through a nuclear reaction to become stable. This nuclear reaction is called radioactive decay, or it's also known as radioactivity. The nuclear force is an attractive force that acts between all nuclear particles that are extremely close together, such as protons and neutrons in the nucleus. At these short distances, the nuclear force dominates over any electromagnetic repulsions from the protons and holds the nucleus together. But again, if you don't have the right ratio of neutrons to protons, the nucleus then becomes unstable and will go through the process of radioactive decay. So that begs a couple of questions. What is exactly a stable versus an unstable nucleus? Like, what does that look like? And what exactly is radioactivity and the different kinds of radioactivity? Well, by definition, radioactivity is the decay of an unstable atomic nucleus followed by the release of radiation. The radiation can take the form of a particle or the form of energy, which we will discuss in a minute. So what makes a nucleus stable or unstable? The stability or instability of a nucleus is related to the structure of the nucleus and the balance of forces that hold it together versus those that tend to make it fly apart, like proton to proton interaction. Protons are positively charged. When like charges are next to each other, they tend to repel each other. So a stable nucleus has the right ratio of neutrons to protons. This ratio for elements 1 through 19 on the periodic table, the ideal ratio is about 1 to 1. So one proton for about one neutron for every one proton. As you get into the heavier elements, elements 21 through 83 on the periodic table, that ratio of neutrons to protons should be about 1.5 neutrons to 1. Remember, it's an average, so that's where we get the half. You can't really have a half a neutron. But at about 1.5 to 1 neutrons to protons, elements 21 through 83 are nice and happy with a stable nucleus. Elements that have atomic numbers from 20 to 83 are what we call the heavy elements. And that's why the ratio is different. The ratio is 1.5 to 1 because of the repulsive forces between the protons. There's more protons, so the stronger the repulsion force between those more protons, that means there's more neutrons needed to stabilize the nuclei. If the ratio is off, then the atom's nucleus is unstable, and an unstable nucleus will spontaneously change. Scientists use the word decay for that spontaneous change to become a more stable nucleus. It does so by emitting a particle or particles and or energy, which are collectively called radiation. Now, if you plot the number of neutrons versus the number of protons for various elements, you see that the neutron to proton ratio, like I said, equals 1 for elements up to atomic number 20, right? Within this region is a line of stable nuclei. We call this the band of stability. Elements above the band of stability have too many neutrons, which decreases the strong force and destabilizes the nucleus. Elements below this band of stability have too many protons, increasing the repulsive force, right? Too many protons, all those protons don't want to be next to each other, which destabilizes the nucleus. All nuclei with an atomic number above 83, so 84 and up, are unstable, and some more so than others. So if you look at a periodic table, all of the elements above 83, so 84, which is polonium, and above, there aren't, in any of these elements, there are so many protons in these elements, right? Polonium would have 84 protons, astatine would have 85, radon would have 86, right? So everything above 83, so 84 and up, there's so many protons that there are no number of neutrons that can glue that nucleus together. The repulsive force is just too much. So again, elements 1 through 20, up here to calcium, that ratio of neutrons to protons is about 1 to 1. 21 through 83, that ratio of neutrons to protons is about 1.5 to 1 to make the atom stable, make the nucleus nice and stable and happy. But after that, elements 84 and up, they are all radioactive because there are just so many protons in that nucleus that they're all unstable nuclei. So then this, of course, leads to, what happens when that neutron to proton ratio isn't ideal. Well, there are several different things, actually, that can happen depending on whether there's too many neutrons or too many protons. Alpha decay happens when too many neutrons and when there are too many neutrons and too many protons inside the nucleus. So we have a nucleus that has too many neutrons and too many protons. It makes the nucleus unstable, and so the atom will spontaneously go through a process of radioactivity or radiation emission, and it will go through what we call alpha decay. If you have too many neutrons in your nucleus, if you're an atom, you'll go through beta emission. Gamma radiation, which is an energy, not a particle, accompanies alpha and beta decay. So if an element's nucleus goes through alpha decay, it will also emit this energy called gamma radiation. If it goes through beta decay, it will also emit this energy called gamma radiation. And if you have too few neutrons, your nucleus might go through electron capture or positron emission. So that's just a bit of a review and then an introduction of what we're going to discuss in lesson 802, radioactivity and half-life, in more detail.